Hello, today I would like to present our project titled Personal Face Identification in Photo Galleries using Deep Neural Networks. In our class, we built CNN models to classify animals or objects. That led us to a new question. Can CNNs recognize something more complex like human faces? So we challenged ourselves to build a model that can find my own face in a gallery of many others. We explored two approaches, using a pre-trained face recognized model and building a CNN from scratch. Today, we'll walk through both methods, compare their performance, and share what we learned. Here is a brief overview of our presentation. We collected around 250 images of twice Nyan and 300 of others for our datasets. Then the images were split into training, validation, and test sets for both approaches. A typical face recognition pipeline consists of three main steps: face detection and preprocessing, extracting a vector representation of the face, and embedding comparison using distance metrics. We referred to a paper of the creator of DeepFace and tested some of the top performing configurations available within the DeepWork framework. Among 16 model combinations we tested, the MTCNN plus FaceNet 512 plus L2 combo delivered the best accuracy of 97%. MTCNN, multitask cascaded convolutional networks, is a cascade of CNNs, PNet, RNet, and ONet, that each performs three tasks: classification, bounding box regression, and landmark localization to detect and align facial landmarks. FaceNet 512 passes the input image through multiple convolutional layers to extract distinctive facial features. At the final layer, it outputs a 512-dimensional vector normalized with L2. FaceNet 512 is trained to perform best on online faces, so it fits MTCNN very well. Additionally, because the model was trained using triplet loss to minimize the L2 distance between embeddings of the same person, using Euclidean L2 distance for comparison is the most natural and effective method. Euclidean L2 distance calculates the square root of the sum of square differences between two vectors. Like other distance metrics, it outputs a non-negative value representing how far apart the vectors are. The custom model we designed can also be divided into three main steps. First is face detection and pre-processing, where faces were located, aligned, and normalized in the image. First is face detection and cropping, where the pre-trained model locates the faces and crops the image. Next is embedding extraction stage, where the CNN converts faces into fixed size vectors. And finally, embedding comparison. Based on the three steps framework, we conducted experiments by selecting different models and algorithms for each stage. We used the face recognition library to detect faces with HOG or CNN-based detectors. Using face locations, we extract the face coordinates and crop the images with PIL. This removes background, helping the model focus on facial features. Then we applied data augmentation, resizing, flipping, rotation, and brightness contrast adjustments to reduce overfitting due to insufficient training data. These augmentations were applied only to the training data, not to the validation or test sets. Next, we fed the crop face images into our model to generate 128-dimensional embeddings for each face. Rather than comparing raw pixel values, this embedding process allowed us to capture more meaningful facial representations. With these embeddings, we could compute distance between vectors, making it possible to quantitatively measure how similar two faces are. Our CNN architecture consists of 4 convolutional blocks extracts features. Global average polling reduces to 256 dimensions. A linear layer reduces it to 128. And L2 normalization produces the final embedding vector. To identify Nyan, we built a binary classification model and tested these four approaches. This method uses a CNN with the classifier. We reduce the 128 featured vectors size, apply value, and use dropout to prevent overfitting due to our small dataset. The model outputs a logit which is converted to a probability using a sigmoid function. This method uses PCA for dimensionality reduction, followed by logistic regression for classification. Though the output is similar to the previous method, the process is simpler and more efficient. This method uses PCA and a SVM with an RBF kernel. SVM works well with small datasets, so we choose it for our 50 sample testset. The RBF kernel improves generalization by capturing complex patterns as shown in the visualization. This method uses image similarity for classification. We first created an anchor by averaging embeddings from Nayon's images. Then we compared a test image's embedding with the anchor using cosine similarity. If the score exceeds the threshold, the image is classified as Nayon. This slide summarizes the results of all four methods. Each achieved around 85 accuracy with the deep learning model performing best. The simple cosine similarity method also showed strong results. We tested the system on the group Ive Anyujin, who wasn't in the training set, using a gallery of 250 random images. Using cosine similarity, the system identified her with 91.9 accuracy, showing strong generalization. This slide compares the pre-trained and custom models. The pre-trained model, MTCNN plus FaceNet 512 plus L2 distance, achieved 97% accuracy. And the custom model used face recognition library and a CNN for 128D embeddings with the best classifier reaching 85% accuracy. This table provides a direct comparison between the performance of pre-trained models and our custom designed model. This slide compares pre-trained models with our custom model. Pre-trained models are accurate but slow and resource intensive. Our custom model, though trained on a smaller dataset, is much faster and practical for real-world use. Thank you for listening.